So far, our focus has been on linear regression models to describe quantitative response variables. In this video, we'll start to turn our attention to categorical response variables by developing some key ideas within probability. We have data on the functionality of a piece of equipment used in constructing space shuttles. These pieces of equipment, which are called O-rings, are used in sealing parts of the shuttle. We have data on a variable called broken, which is equal to 1 if an O-ring was broken and equal to 0 if the O-ring was functional. We also have data on the temperature the day the equipment was tested in degrees Fahrenheit. A natural research question that arises is, how does temperature affect the chance of an O-ring being broken? There are a lot of different temperatures present in this data set, so we'll simplify our approach slightly for now to only consider low versus high temperatures. Here we've categorized temperature as low when the temperature is 65 degrees or lower and high otherwise. The cases broken down by temperature and broken status are tabulated here. To get some initial understanding of the rarity of O-rings being broken, let's first ask, what is the chance that an O-ring will be broken? We can represent this in probability notation as P of broken equal to 1, where the P stands for probability or chance. The information inside the parentheses describes the event that I want to know the probability of. We don't have the whole population of all O-rings ever made and tested, but we can estimate this chance of being broken from our sample of O-rings. There are 138 total O-rings in our sample, and of these 138, 9 broke. So our estimate of the probability of an O-ring breaking is 9 out of 138, or 6.5%. We can similarly ask about the probability of an O-ring being functional. Out of the 138 O-rings, 129 were unbroken. So our estimate of the chance of being functional is 129 out of 138, or 93.5%. Know that this probability is 1 minus the first probability of being broken. In general, for binary variables like the broken variable, the probability that the variable equals 1 will be 1 minus the probability that the variable equals 0, and vice versa. In comparing the chance of being broken to the chance of being unbroken, it's actually useful to introduce a new concept, a concept called odds. If P is the probability of an event, then the odds of that event is P over 1 minus P. The odds can be interpreted as the answer to the question, how much more likely is the event to happen than to not happen? For example, the odds of an O-ring being broken is the chance of it being broken, 0.065, over 1 minus that chance, 0.935. This odds is 0.07 and tells us that an O-ring is 0.07 times as likely to be broken than not broken. In other words, not very likely to be broken. The odds of an O-ring being not broken is the chance of it not being broken, which is 0.935, over 1 minus that chance, which is 0.065. This odds is 14.38, which tells us that an O-ring is 14.38 times more likely to not be broken than to be broken. So, odds are a useful way of telling us how much more likely something is to happen than not happen. And they will feature more extensively soon when we consider new types of regression models that are appropriate for binary response variables. So now that we have some understanding of the broken variable on its own, let's return to our research question, which involved looking at the relationship between broken and temperature. So instead of asking, what is the chance that an O-ring will be broken, where this estimate was 6.5%, we can now ask, what is the chance that an O-ring will be broken given that the temperature is high? In probability notation, we write this as probability that broken equals 1, given that temperature equals high. And the vertical bar means given. If we are given the information that the day's temperature is high, above 65 degrees, This changes our estimate in a very important way. Now, we only consider the cases in our data set where the temperature was high. This is 114 cases instead of the full 138. And of these 114 cases, 4 were broken. So the conditional probability that an O-ring will be broken given a high outside temperature is 4 out of 114, or 3.5%. This is described as a conditional probability because the probability of interest, a broken O-ring, is now under the condition that the temperature is high. Note that once we have this information that the temperature is high, this conditional probability is a bit different. It's lower than the original probability of an O-ring being broken, which again was 6.5%. This means that high temperature is informative about helping us guess whether an O-ring will fail. We can also compute the odds corresponding to this conditional probability. If we call the conditional probability that we just estimated P, this odds is P over 1 minus P. Here, the odds of an O-ring being broken, given a high temperature, is 0.036, which means that if the temperature is high, an O-ring is 0.036 times as likely to be broken as not broken. So we can similarly ask about the conditional probability of an O-ring being broken given that the temperature is low. Here, the condition of temperature being low means that our estimate should look only at the 24 cases where the temperature was low. Of these 24 cases, there are 5 broken O-rings. So we estimate this conditional probability to be 5 out of 24, or 20.8%. As when temperature was high, note that this conditional probability is different from the original chance of an O-ring being broken. This time it's a fair bit higher. This is another indication that temperature is informative about the chance of an O-ring being broken. And as before, we could summarize this information with an odds. The odds of 0.263 tells us that when temperature is low, an O-ring is 0.263 times as likely to be broken as not broken. So let's form some conclusions from these calculations. Whether we look at the probability of an O-ring being broken or the corresponding odds, we see that an O-ring is much more likely to break when the temperatures are low as compared to when the temperatures are high. The 20.8% conditional probability is much higher than the 3.5%, and the 0.263 odds is much higher than the 0.036 odds. So it turns out that all of this information underpins an infamous event in NASA's history.